This is me again. I didn't have a chance to go over the post-lab assessment on the Newton's second law of motion, and I thought that was going to be important as a way to close up chapter 4 and 5 before the quiz on Monday. So if you have a chance to review this, that would be great. And you don't need to give me this lab handout back on Monday. So that's it. And the same with the work kinetic energy theorem. We'll start something new on Monday, and I will not have the chance of going over the lab handouts that I gave you before. So that's why I want to pretty much complete and discuss this with you without going over 120 handouts I have to read it. But basically, first situation, you have an object that is moving, subject to a net force, and suddenly this net force becomes zero and remains zero, right? So that's the situation. So imagine you have a block, and there is a net force, put a net force in this direction. This is the net force. So the net force could be the result of a bunch of things. Could it be weight? Could it be weight sum to some thrust force if you think about a rocket, drag forces on it. But suddenly the situation is such the net force goes to zero. If there is a net force, also it means implies there is an acceleration in that direction. So if suddenly this becomes zero, so what's going to happen? Well, if the net force is applied for a while, it means that certainly there is also a velocity vector um, that is going on. So either the velocity vector has the same direction as that of the net force or not. Like you could have both vectors opposing each other. I can give you a situation. So let's say you have a car, you have a car or a car that moves to the right with a velocity v, assume there is no friction. So the car is gliding on ice, let's say, and is gliding to the right with some velocity v, and then suddenly there is some net force that opposes the motion of the car, like the car presses some sort of a brake that goes through the ice. So here's the net force, so which means the net acceleration, which is associated with the net force, is also opposing, um, is also in the same direction of the velocity of the force vector, and opposes the direction of the velocity vector, which means um, your car will decelerate and will slow down and eventually go into a stop. So not necessarily your acceleration and velocity vector should have the same direction, but hypothetically speaking, let's say you have a net force that gives you an acceleration in that direction. Let's just, for the sake of argument, assume the velocity has the same direction as that of acceleration, which means your object is speeding up, right? And suddenly, this comes to a zero. So what happened? Well, according to Newton's first law of motion, right? If an object is at stationary, or if it's moving with a given velocity, and the net resultant force on it is zero, it shall remain at rest or moving with that same velocity forever and ever. So if this situation happened, we stopped abruptly? No. We reduce speed? No. We increase speed? No. We correct continue at constant, correct continue, correct continue. I think it's continue at a constant velocity. This is the correct one. I think the solution went there. Continue at a constant velocity, yes. Reduce speed gradually, no. You have an elevator decelerate to a stop at a floor during the deceleration of an elevator traveling upward. So let's make the situation you have an elevator here, right? And there is some individual in there. So let's think this person just for now is standing on a scale. There is a scale right here. So um, so the elevator moves upward, right? Let's say it has a constant speed, moving upward with a constant speed. So if the speed is constant, the net force on the person is zero. So if you do a free body diagram for that person at that moment, so what you really have on the person, so the free body diagram on the person is the weight of that person, which is mg, and you have the reaction of the scale on the person's foot, right? Call that normal force. And if the elevator moves upward, then with a velocity that's constant, the acceleration is zero, then normal minus mg 0. So you have the normal being equal to the weight of that person. But if suddenly now the elevator goes from 1 meters per second to 0 meters per second, so there is some deceleration, and that's what's going on here. During the deceleration of an elevator traveling upward, okay, so the elevator is moving and then decelerates and comes to a stop. What is the normal force on the feet of the passenger? So how do you do that now? Well, you do a free body diagram. That's the answer to all questions, or at least the beginning of the answer. So you put the weight of that person, you have the normal force upward always, and the elevator moves in this direction, right? But the acceleration, so you call this direction positive, okay? Because that's the direction of motion. But the acceleration of the elevator is negative. In other words, the velocity vector is still positive, but the acceleration has an opposite sign. So you have a deceleration going on. The elevator is slowing down. So how do you do your free body diagram in this case? Well, normal is positive, gravity is negative, right? It's pointing down. Equal mass times the acceleration. But the acceleration is a negative number. So let's say the acceleration is 1 meter per square second in absolute numbers. So what you should plug here is negative 1 minus a. Okay, so n minus mg is equal negative ma. So the normal force is equal to mg minus na, which means if the elevator is moving upward and decelerates, the normal force, which is the scale reading, the normal force is less, right? Is less than the weight of the person. So the person looks down the scale. Let's say the person has a weight of 700 newtons. So when you look down the scale, the person will read 650 newtons, let's say, okay, depending on the acceleration, which means it's less than the weight. So you feel kind of a less weight than it is. And if you had gone in amusement park and have gone in the situation of going up and then suddenly you go to a stop when you reach the top of an ascending um, process, you feel kind of a stomach is gone, right? You feel weightless. That's the idea. And now the situation is different here. During the deceleration of an elevator, now if the elevator goes downward, let me erase this part here so we can do that part. So the elevator is going downward. Now the elevator is traveling downward, right? With a velocity, let's say 1 meters per second, but going downward. What is the normal force? Oh, and you have a deceleration. So the elevator is going down, let's say going from the third floor to the first floor, and then decelerates to stop at the first floor, right? So it goes from 1 meter per second to 0 meters per second. So which means the motion is downward. It's called the downward positive because that's the direction of motion. But the acceleration is opposite to that. The acceleration is up because it's slowing down, see? And the acceleration vector must be opposite to that of the velocity vector. So when you do your free body diagram, which is done right here, and you apply the Newton's second law, mg minus n is equal m minus a. Why is that? Well, if I'm calling the direction downward positive, mg now has a positive sign, normal has a negative sign, the acceleration is up, opposite to the positive sign, which means you have to plug a negative sign in there. So when you rearrange these equations, you have n is equal mg plus ma, which means when you have this situation, the elevator is going down and comes to a stop, you feel press yourself downward, which means your scale, you read more than your weight. So if you had 700 Newton, the scale is going to give something more. And you have different situations like that. So if the elevator, suddenly the cables snap and fall, I mean, you don't feel any reaction, right? You are in free fall in there. Okay. 7.7 kilograms objects rest on a level floor with a coefficient of static friction given. Okay. Coefficient of static friction is 0.35. What is the minimum horizontal force? So now, if you apply an horizontal external force, the static friction matches up and the block doesn't move. And then you keep increasing this external force and the static friction keeps, matching up to the point the external force is bigger and the static friction can't do anymore. So there is a external force that if you go above the maximum value of static friction, the block will move, and that's what the problem wants you to find for. Well, the static friction has a maximum value, and that is given by the coefficient of static friction times the normal force. So in this case, the normal force is equal mg, and then your problem is simply putting this times 7.7 times 9.8, and then you have your solution done. So the D is you have a classical situation of that we've done in the lab so many times. And let me do the part in which there is friction. So the situation without friction, you just bring the normal force to zero, but this is pretty much lab exercise. We did this so many times. What you do a free body. So if there is friction, if there is acceleration, you must build the free body diagram on both situations. So you have a block. The forces are the weight, the normal force. In this case, normal force is equal to the weight. You also have a tension force, and you have a kinetic friction force. Kinetic friction is equal to the coefficient of kinetic friction times normal force. In this case, and only in this case, this is what it is, okay? So the kinetic friction is basically 0.5 G Newton. So when you apply the Newton's second law to this block, T minus 0.5 G, right? T minus 0.5 G, which is the kinetic friction, is equal mass of the block times acceleration. And then you save that equation. Then you go to the falling block. So the falling block, the forces on it are 9G and the tension that has the same magnitude of this. The direction of motion is down, you have an acceleration, so that when you apply Newton's second law in here, 9g minus t is equal 9a. And then what you do next is to combine those two equations. 9g minus t is equal 9a, and then solve by substitution. I think one easy way of doing this is to add those two equations. So 9g, t cancels out, minus 0.5g is equal 5a, and then you can solve for a. Once you solve for a, you solve everything. Okay, good luck.